Professor Richard Jozsa. Professor Richard Jozsa is the Leigh Trapnell Chair in Quantum Physics at the University of Cambridge. He is a pioneer in quantum information science and co-inventor of the Jozsa quantum algorithm and one of the co-inventors of quantum teleportation. His work was recognized in 2004 by the London Mathematical Society with the award of the Naylor Prize for his fundamental contribution to the new field of quantum information science. Professor Jozsa received his DPhil in mathematics, twistor theory, at Oxford under the supervision of Sir Roger Penrose. He has held previous positions at the University of Bristol, the University of Plymouth, and the University of Montreal. His research interests include the relationship between the no-signaling principle and other aspects of quantum theory, and applications of quantum information theory, foundational questions in quantum information theory, quantum theory, probability theory, and quantum gravity, the theory of quantum channels, and novel cryptographic applications of quantum information. Today, he'll be talking about classical simulations of quantum computations illustrated by Clifford circuits.
And I'd like to talk more specifically about quantum computation, and in particular the idea of classical simulation of quantum computations. And then I'd like to illustrate the great richness of this idea by a particular kind of computations which are called Clifford circuits, and I'll explain what these are as we go along. Okay, so I'd like to begin with some remarks about background and context. We often hear that quantum computing is more powerful than classical computing, which kind of drives the whole subject, but indeed we would like to understand in more detail what the relationship is between classical and quantum computing power. We'd like to develop tools and techniques for studying that, and indeed try and isolate the quantum features that make quantum mechanics better for computing than classical effects, so that we might be able to exploit these properties in the design of quantum algorithms that have this enhanced kind of power. And the study of this notion of classical simulation of quantum circuits provides a mathematically precise way of addressing these rather vaguely formulated questions, so it's of great interest in the foundations of the subject. And the notion of classical simulation, perhaps I should just say intuitively what this is. Suppose you're given a description of a quantum computation. For example, it might be a list of gates that you are to apply to some given input state. Then you can write all this down on a piece of paper and give it to your quantum technician and ask him or her to implement this in the quantum lab and come back with the answer for you. But suppose you don't have a quantum lab and you want to know how much classical computing effort is required to simulate the output of the quantum computation, only working with classical means. And so that's the idea of a classical simulation, and you say the classical simulation is efficient if the classical computational resources are pretty much the same as the quantum computational ones required. So efficient simulations means that the quantum process is not really providing you with a computational benefit, because you can mimic it quite well classically just as well, given a description of what the quantum process is doing. So this idea of classical simulation can be used to explore the relationship between classical and quantum computing. As I say here, from above and below, we can provide evidence that some classes of quantum computations, quantum circuits, are hard to simulate. They require a lot of classical computing effort in order to mimic them. And hardness is notoriously difficult to prove of anything in complexity theory. For example, the issue of P versus NP, we still haven't proved that NP is different from P. So in similar vein here, it's very hard to prove that any quantum computations are hard classically, but instead we resort to a slightly indirect tack and show that if you could efficiently simulate some class of computation, then that would imply the collapse of some classical complexity class. For example, if you could simulate a certain computation classically, it would mean that P would equal NP, which is implausible, and therefore you regard that as strong evidence that you won't be able to perform this simulation efficiently. But on the other hand, you can look for classes of quantum computations that can be simulated efficiently classically, and these, from a computational point of view, are lame or uninteresting because they don't provide any computational benefit. On the other hand, they're very interesting from a foundational point of view because they can involve very rich quantum effects, and it shows that the relationship between classical and quantum computing is actually a very rich and complex one, and several such classes are known and involving different interesting simulation techniques. So it's not just that classical computing or that quantum computing is more powerful than classical computing, but there's this rich relationship which we want to explore and characterize as best we can. So, so let me move on to saying more precisely now what I mean by a classical simulation of a quantum circuit. So as I've sort of alluded to before, what we're given is a description. It's classical information. It's a description of a quantum computation, which you can think of as a list of gates and the lines, the qubits on which they act, some input state, which will normally be a computational basis state labeled by a bit string, or more generally we'll consider product states, and you need to specify what the output is going to be. So normally you measure a single line for a decision problem, for a yes-no answer, or maybe more lines, say, several lines for more complex kinds of answers. And the size of this computation is characterized by the size of the circuit, which I call capital N, which is just the number of gates. It's the number of steps of quantum computation that you need to do to perform this quantum computation. And then, so this is all classical information about the quantum process. So we want to ask, how much classical computing effort does it cost us to produce the output that this quantum process would do? So we can ask for different kinds of simulations, a so-called weak or a strong simulation. So a weak simulation is simply to provide, by classical means, a sample of the output probability distribution of this process, because quantum processes are generally probabilistic. But a strong simulation asks for more. We want to not just sample the distribution, but we want to calculate the output probabilities themselves, or marginal probability distributions as well, if there are many lines in the output. Okay, so note that a weak simulation is what the process itself gives you. If you run this quantum process, it will provide you, if you run it once, it will provide you with one sample of the output, but it won't provide you with the actual probabilities. You have to work much harder, even with the quantum process, to get that. So that's just a general notion of simulations, but the notion of efficiency of simulation is going to be crucially important here. So a simulation is efficient by these classical means if you can do the classical simulation in polynomial time. In other words, the number of steps of classical computation that you need has only a polynomial and not, say, an exponential overhead in the number of steps that the quantum process itself uses. So in complexity theory, it's usual to accept polynomial overheads as okay, as not being problematic, but exponential overheads are unacceptable. And in fact, it's quite easy to see, and we'll allude to this later, that any such quantum description can be classically simulated, even strongly, but not efficiently, if you allow exponential overhead in the resources with exponentially n number of steps. So this polynomial overhead is going to be this subtle, crucial ingredient here that will be of great interest. So for example, if you have a weak classical efficient simulation of this thing, it means that this quantum process is providing you with no classical computing benefit. Gilles, yes. So if you can weakly simulate the thing classically, it means that you can you can produce whatever this quantum computation is doing classically with only a polynomial overhead in resources, which is an acceptable overhead, so this quantum computation is not of interest in a computational scenario. Okay, so we'll be interested to know when you can and cannot do this sort of thing. So the first thing is that to note is to make some remarks about strong versus weak simulations. So an efficient strong simulation implies an efficient weak simulation. Now this is not immediately obvious. If you can calculate all the probabilities, does that mean you can sample the distribution? Well, it's fine so long as you haven't got too many output lines. So suppose you have n output lines, then there are 2 to the n probabilities, because they each have output 0 or 1, say. So even if you can calculate each probability efficiently, there's exponentially many of them. You can't calculate them all efficiently. So how do you sample the distribution efficiently? So this implication is not immediately obvious. But if you can calculate the marginals as well, there's a little trick to do it here. So the probability of x1 up to xn can be written as this sequence using Bayes' rule of conditional probabilities. It's x1 times x2 given x1, x3 given x1, x2, and this tower here, because each of these conditional probabilities is a quotient of marginal probabilities, and then they all kind of cancel out and leave you only at the top end with all of them here, which is what you've got here. So now you see how you can do this efficient simulation. You calculate the probability of x1, you sample it and get a value. Then you calculate the probability of x2 given the seen value and sample that. And then you calculate the probability of x3 given the already seen values of x1 and x2 and work your way up this tower. And each of these conditional probabilities is just the quotient of marginals. And there's n steps in this tower, and the bottom line of each one is the top line of the previous one. So, you know, a tiny amount of thought shows that all in all, you only need to calculate n of the marginals. Even though there's exponentially many probabilities, you only need to calculate n marginals and sample n times, so it's linear in n, so it's efficient. So indeed, so long as you can calculate marginals as well, you can get this relationship. But the other way round, perhaps unsurprisingly, we expect that weak simulation does not imply strong simulation, efficient simulation. So to argue that, consider a Boolean function from n bits to 1 bit, so there's 2 to the n possible values, and let capital A be the number of inputs, number of n bit strings for which f of x is 1. Then you have the usual quantum oracle implementation of this Boolean function, and you can consider the following simple quantum process. You start with n qubits and an extra output qubit. You apply the Hadamard transformation n times, which transforms each of these zeros into a superposition of 0 and 1. Then you run the function on it. So in other words, you're evaluating the function in superposition in a very simple way on all the inputs. And then you measure the final output qubit. So the probability of seeing 1 is clearly the number of 1s divided by 2 to the n. Okay, so this is a simple quantum process, and the output probability is just the fraction of values that are 1. So a weak simulation of this process is easy. You just, instead of doing all this in quantum superposition, you classically randomly choose an n-bit string, work out its value, and output it. So clearly, the probability of outputting 1 is just the chance that you get a 1 value, which is a over 2 to the n. So that's very simple. But a strong, efficient simulation is likely to be extremely hard. And you can argue that in the following way. So if you can do a strong, efficient simulation, it means you can calculate this probability to good accuracy. In other words, you can calculate the value of a in polynomial time in n. So in particular, you can decide if a is 0 or not, if there are any values of x with 1. And this solves the famous satisfiability problem, which would show that p is equal to np if you could do this in polynomial time. So if you could strongly, efficiently simulate this process, then p would equal np. But even more, you could not only decide whether a was 0 or not, you actually get its value, and you can count the number of of places where the function is 1. And that's much, much harder classically. It's so-called sharp P complete. And you would get that sharp P can be done in polynomial time. So we say that strong simulation of this process is sharp P hard. So in other words, we relate this process to a collapse of classical complexity classes, which is very implausible. So I want to just slightly elaborate on this terminology. When I use the word efficient, I mean it can be done with classical resources in polynomial time, be it for weak simulations, it's classical probabilistic resources, and for strong simulations, it'll be deterministic resources. And SAT is the standard satisfiability problem. Given a Boolean function from n bits to 1 bit, I want to decide if there is an input that has output 1, as we just saw. And sharp SAT is the same problem, except I want to count the number of places where the output is 1. So that's that capital A we had. And then I'll say a simulation task, capital Pi, say, is NP hard or sharp P hard if, given the ability to do the simulation task, you can solve these two problems. And you allow yourself further polynomial classical computation, if you like, that's sort of a modest amount, to translate, say, instances of the satisfiability or sharp SAT problems into the simulation task, which you then do. So in that case, if you have an efficient simulation of this task pi, then if it's NP hard, it would imply that P equals NP, or if it's sharp P hard, it would imply that sharp P equals P. So this is how we provide strong evidence that some simulation task is hard, that the process it represents is actually providing us with computing power that vastly extends classical computing power. Okay, so we'll be interested in figuring out when certain simulation tasks are hard in this sense, or if they're efficiently simulatable. Okay, so now to consider some issues of actual simulation techniques. The first thing to notice is that given any quantum circuit whatsoever, you can always simulate it strongly, but not necessarily efficiently. Because after all, a quantum circuit is just a starting state and a sequence of quantum gates. And a state is just a vector, and the gates are just linear operations on the vector space that you're in. So by simple linear algebra and matrix multiplications, you can always compute the components of the evolving state. But the trouble is, for each extra qubit that gets introduced into a system, the dimension of the whole thing doubles, and the number of components that you're working with in this computation typically grows exponentially with the number of steps, the number of gates you've applied. So for example, if you have an n-qubit state which has these components, ci up to in, there's 2 to the n complex numbers there. If you apply some gate on the first 2 qubits, you get a new quantum state whose component is c primed, and a simple algebraic calculation shows that you get the updated components from the original ones just by a simple matrix multiplication on the first 2 indices here. But the trouble is, to work all of these out, you've got to repeat this computation exponentially many times for all possible values of the remaining strings. So although we have a simulation method, it's not efficient. And hence the quantum process in principle provides us with this enhanced computing power. But if all the states in the computation are promised to be product states, which means these C's factorize as just a product of single index vectors like this, then when you update this calculation here, you can deal only with the alpha and beta and take all the rest along for the ride. So the computation now can be done in constant time. It's just a 4 by 4 matrix multiplication here, and then you refactorize the answer into a product of 2 things, which it must be because it's promised to be a product state. So all that can be updated in just polynomial time. So this shows that if the quantum computation has no entanglement, if the states are product states at all times, then you can never gain a computational advantage in quantum over classical computing. So the presence of entanglement is certainly necessary to have quantum computational benefit, but it's not sufficient. It's not sufficient. It's not sufficient in the sense that although it's easy to describe here that you need entanglement, one can come up with interesting classes of quantum computations which still involve a lot of complicated entanglements, but nevertheless can be efficiently simulated by more clever tricks than just this. There are many other ways of classically simulating quantum computations, and in particular, a very good sort of toy example to study are these so-called Clifford computations, which are quantum computational processes involving only these so-called Clifford gates, which, if you've done a course in quantum computing, you've probably already met, but let me sort of describe briefly what they are. So we start with the Pauli group. So this is the 1-qubit Pauli matrices, which are generated by X and Z, as we've already seen this morning, and the Y operation is the product of these two, and you add I as well. So these matrices generate a group, a small group of 2x2 matrices. Then you have the n-qubit Pauli group, which are tensor products of these things over n qubits. So these are unitary matrices of dimension 2 to the n. And a Clifford operation on n qubits is just defined to be a special kind of unitary operation which satisfies this algebraic condition that if you conjugate any product of Pauli's by it, you don't just get any old unitary back, but you get always another product of Pauli. So that's a very special condition on this unitary operation C. So in terms of group theory, the Clifford group, so all such C's form a group, which is easy to see, and it's the normalizer of the Pauli group in the set of all unitary matrices of dimension 2 to the n. Now, this is a kind of abstract algebraic characterization. It's possible to analyze exactly what unitaries you get in this case, and one can prove, but I won't go into the proof here, that an n-qubit operation is a Clifford operation if and only if it can be built up as a circuit of Hadamard gates, this pi over 2 phase gate, which I'll call S, and controlled Z gates. So it's a very simple and nice characterization, and it's exactly equivalent to this algebraic condition here. So these have occurred in many fundamental places in quantum computation and information theory, and we'll look now at circuits involving just Clifford gates and some interesting extra ingredients as well, which I'll come to in a moment, to illustrate the richness and variety of simulation techniques you can have. So the extra ingredients I'm going to have, in addition to having circuits of these basic Clifford gates, I'm going to consider inputs. So I've given them all names here so you can keep track of them, because it gets a bit complicated to remember which one we're considering. So the inputs can be standard basis states, or they can be product states. So I'll denote as in standard or in product. I'm going to also allow measurements within the circuit before the end as kind of computational steps rather than producing outputs. So I can have circuits with no measurements along the way, or I can have adaptive circuits where you do quantum measurements along the way, and subsequent gates in the circuit are allowed to be chosen adaptively according to the outcomes of prior measurements. So this is a kind of probabilistic adaptation as you go along. And you can have two kinds of simulation, weak or strong simulation, efficient, so simulations will always be efficient now. And the outputs, you can have single output line or many output lines. So there's these 4 categories of things, and so there's 16 possible combinations, and it's possible to characterize the simulation complexity of all these combinations, and it's interesting to see how radically they vary with sort of modest changes of the rules of the game here. So it shows that the origin of computational power is a very subtle thing, and it can change very, very wildly according to just slight changes of what you're allowed to do. Okay, so I guess first a remark about no measurement and adaptation. There's a kind of intermediate category here. You can allow measurements during your computation, but not allow the gates to be chosen adaptively according to the measurement outcome. So you can have non-adaptive measurements, but still use measurements along the way to generate different kinds of computational steps. However, that's exactly the same as no measurements at all. So non-adaptive, that is measurements along the way and subsequent gates do not depend on measurement outcomes, is exactly the same as no measurements at all in our context of Clifford circuits, because if you have a circuit here, these are qubit lines, and if you measure one of them at some point, that's exactly the same as not measuring it, but having an extra ancilla in state 0, and you do a controlled X, which is a Clifford operation. You do a controlled not operation, which effectively copies, it does a quantum copying of this state onto this line and decoheres this line. And so then you don't use this one again, but then the state that comes out here is probabilistically equivalent to what you'd get here with the measurement. So we get this equivalence here. Okay, so let's now start considering our different cases and begin with the simplest case. And I want to consider first the scenario of only single output measurements. So the answer is just yes or no. It's just a decision problem, which is the most commonly encountered case in computational applications. So the simplest case, which is really a variant of the so-called Gottesman-Knill theorem, is that if the inputs are just standard computational basis states, the computational steps are just Clifford gates. We don't allow measurements along the way. We have a single output line. Then strong simulation of this process can be done classically efficiently. So it's in classical P. So such computations give you no computational power over classical computing. And I want to give or outline two ways of proving this result, because the two proofs are different and they lead to inroads into different cases for the further generalizations. So the first proof I call backwards propagation of the final measurement. And so the idea here is that you start with your Clifford circuit, which is just made up of a circuit of these H phase, pi over 2 phase gates, controlled Z gates. It has some size n, some number of gates, some number of qubits, and the input state is just one of these computational basis states. And the output probabilities are just P0 and P1, and without loss of generality, we'll suppose they're measured on the first line of the circuit. So if we write Z on the first line and I's on the rest, this is a Pauli product, then the Z operator is just the projector onto 0 minus a projector onto 1. It's the diagonal matrix with 1 and minus 1 on the diagonals. Then it's well known, therefore, that the difference in the probabilities is the expectation value of this operation. So it's the final state of the circuit wedged around this operation, this Pauli product here. But the final state is C times, it's the Clifford operation on the input state, psi 0. And here it is with its complex, with its adjoint here. So if you now view these C's not as operating on the states, but as conjugating Z1, these conjugations act in reverse order. You start with the last one conjugate Z1, and then the second last, all the way back to the first at the very ends. And in each such conjugation, because they're Clifford operations, preserves a Pauli product. So each time you just get some Pauli product, and you can classically calculate what these Pauli products are doing. You can easily do that because these conjugation relations for what the Clifford operations do on Pauli products are just simple things to calculate. And so at the end of the day, this expression looks like this, but psi 0 is a computational basis state, and this is a product of operators. So this expression breaks up into just a product of n 2 by 2 matrix calculations. So you can compute all this in classical polynomial time. and hence you get a proof of this theorem. You can compute the difference in the probabilities, and since they add to 1, then you can get the probabilities themselves. Okay, so this provides one quick and simple proof, but notice that here we're not giving a description of the evolving state in the computation at all. As it were, we're back propagating the final measurement. This Z1 gets propagated backwards to the initial state and gets complicated like this, and then it's evaluated back at the original state there. So the second proof relies on the so-called stabilizer formalism, which was historically the first proof, and this is basically how Gottesman and Knil proved this theorem initially, coming at it from a different point of view. And so the first thing to note is that this direct strong simulation can't be applied because even in simple Clifford computations, the states can get complicated and entangled. So, for example, starting with n qubits in state 0, we apply Hadamard's, we get exponentially many amplitudes here, even though it's a product state. But then if you apply some CZs, it will no longer be a product state, and there will be no small description of these states in terms of their amplitudes. They'll be exponentially complicated. But it turns out that there's a clever alternative description of these states which does remain small. It doesn't grow exponentially. And these are so-called stabilizer state descriptions. So a stabilizer state is any state of n qubits which is the unique state which is stabilized by some subgroup of the Pauli group on n qubits. So not all states are like this. They're very special states. So in other words, the state psi should have the property that there's a subgroup of n qubit Pauli operations such that g of psi equals psi. It's stable. They stabilize the state in this form, and psi is the unique such state. So, so this subgroup, g sub psi, completely characterizes what this state is. It uniquely describes it. So a simple example here is that this Bell state, 0, 0 plus 1, 1, is the unique state stabilized by x tensor x and z tensor z, because x turns zeros into 1, so you get 1, 1 plus 0, 0, and z goes 0, 0 goes to 0, 0, but 1 and 1 goes to minus times 1 and minus times 1, and you get a plus sign again. And this is the only state stabilized by these two things. So this is a description of this state in this group theoretic terms. Okay, so stabilizer states have these properties, and so here's I'm not going to sort of show how these proofs go, but these are the basic facts about stabilizers that allow you to simulate Clifford circuits. So the first thing is that these subgroups of the Pauli group on n qubits, any subgroup can always be described by at most n generators. So only n elements are required to describe it. Even though the subgroup itself can be exponentially large, it's always discrete, but the exponential number of elements are always generated by a small number under products. And so the description is always small. It's polynomially sized. It's linear sized. All the standard basis states are stabilizer states. They're just stabilized by tensor products of z's and minus z's. They're a particularly simple class of such stabilizer states. If you have a stabilizer state, which is stabilized by some bunch of Pauli operations, the g1 to gk here, then if you act on this state with a gate, u of psi, then that's stabilized by the previous stabilizers conjugated by u. So that's kind of easy to see, because if you apply this to u of psi, the u dagger annihilates that, the g1 stabilizes it, and then the u puts the u back on again. Okay, so you can update the stabilizer generators very easily, but the trouble is for general u's, these conjugations will not be Pauli products anymore. So it won't be a stabilizer state. If you do have a stabilizer state, stabilized like this, and if u is a Clifford operation C, then because conjugations by Clifford operations preserve Pauli products, it implies that the updated state, C of psi, must again be a stabilizer state and hence have this small description. And so putting all these things together, it shows that we now have an efficient description of the evolving state in any one of these Clifford computations, which, unlike the components description, is polynomially sized, because we start with a computational basis state. It's described by this small list of generators. We update it by Clifford operations, so the stabilizers are just updated in this way, and they stay small because the operations are Clifford, and hence you get this calculation of the computation in efficient terms. And the final fact about stabilizers is that given the stabilizer description of a state on, say, n qubits, it's possible to compute the probabilities and post-measurement states of any measurement on this state, either on one line or on many lines. Okay, so one can show how to do this in classical polynomial time. So the description, apart from just being a nice, small, compact description, it also allows you to compute the probabilities and post-measurement states of quantum measurements. And hence, putting all these together, we get an alternative proof of the theorem that I quoted. And in contrast to proof A, here we do actually work with a description of the evolving state as we pass through the computation, but it's this rather interesting kind of description based on these stabilizer subgroups. Okay, so the point of introducing these two different proofs is that they allow different generalizations. So remember, we're working with standard input, computational-based inputs, no measurements, and strong simulations. So proof A immediately generalizes to allowing product state as inputs, but it doesn't generalize to having adaptive measurements along the way. So you can see that very easily here. Here in the proof. So if you recall how this proof works, we go to here, and at this stage here, the crucial point is that this tensor product here matches the product state property of the input. And if these inputs were not computational basis states, but arbitrary product states, this would all still work, and you just have 1 qubit states here, which are more general than the computational basis ones, but the computation here is still just as simple. So you get an immediate generalization here to arbitrary product state inputs, but it's very hard to figure out how to backpropagate this final measurement through a gate that's been adaptively chosen in response to a measurement made earlier. There's no natural way of doing that. And in fact, we'll see later that to replace that by an adaptation there is actually very, very hard. That classical simulation problem is actually sharp P hard, so we don't even expect to be able to do that. So in the case of the second proof, this stabilizer description, although this generalization was immediate, it can't be applied here because general product states are not stabilizer states. So remember, all the standard basis states are stabilizer states, but general product states are not. So this whole process can't even get started in that scenario of general product states. So that doesn't work. But on the other hand, this proof does allow you to generalize to a situation where you still have standard input states, but you now make measurements along the way and you adapt gates. Because since we're computing the evolving state, using F here, if we make a measurement along the way, we can compute the probabilities and compute the post-measurement state and carry on with our simulation. And this all still works in this formalism. So you can adapt here. It's down here, sorry. So you can have an adaptive process here, but you can't have a strong simulation because as you go along the way, you calculate these probabilities, and then you have to toss a coin and choose which way you're going to go. So within the process, you introduce a kind of weak simulation. You have to make probabilistic choices along the way. You can't follow all the different paths from different measurements, because after, say, n measurements, you'd have 2 to the n outcomes. So it's important to just follow some single path through that simulation. So strong becomes weak. So this proof B gives you this interesting thing that if the input states are product states, you allow a full adaptive process, but a weak simulation, that can still all be done in classical polynomial time. Okay, so we have, so we've analyzed a few cases now. We've had inputs being standard computational basis states, we have adaptive processes, and we have weak simulations being classically efficiently simulatable via the stabilizer formalism. So what about making this strong? And what about even keeping this weak but allowing product states here? So both of these turn out to be enormously harder, even though they may appear to be kind of slight generalizations of what we're doing. So first of all, to see that A is actually sharp P hard, suppose you have this situation of just standard input states, but you're allowed to adapt and do measurements along the way, and you have a classical simulation of that, a strong classical simulation, so you can compute probabilities. Well, within those resources, you have Hadamards and zeros, and you have measurements. So in particular, you can generate classical random bits just by measuring h of 0, which is like a fair coin toss. You also have controlled knots and adaptations, so you have a classical controlled knot. You can apply a controlled knot according to whether some other measurement outputs 0 or 1. So at least in a classical context, you can have controlled applications of this, which is the classical Toffoli gate. So, and that's known to be universal for classical computation. So in other words, within these resources, you have universal randomized classical computation. And so a strong simulation of that implies you can compute output probabilities efficiently for any such computation, so you can count the number of satisfying assignments for any Boolean formula just as before. So we can count the capital A that we had before by computing a suitable probability of a classical computation here, a randomized one. So that shows that A here is actually sharp P hard. So for the second one, it's a slightly more subtle kind of complexity. If you only want weak simulations, but you allow yourself to adapt with measurements along the way, and you allow yourself general input product states, then I call this is so-called QC hard, for quantum computing hard, because within the presence of this amount of resources, it turns out you can represent any quantum computation whatsoever, not just the Clifford ones, and hence if you could weakly simulate that classically, it would mean that you could weakly simulate any quantum computation classically, and it would imply that quantum computation is just no more general than classical computation. So it's quantum computing hard. In other words, it would imply that any quantum computation could be classically simulated. So to see how that works is not so hard. You use another fact about Clifford operations, is that if you add this non-Clifford gate, this single 1-qubit gate, which is the square root of the phase gate that had the I there, 1I, call this one T, that previous one was S, so T is like the square root of S. This set of gates is universal for quantum computing. So hence you can represent any quantum computation with these gates, which is slightly more general than Clifford gates, because this T is not Clifford. So the issue now is, well, we can apply this gate T using a little bit of trickery with Clifford gates and the extra facility of input product states. So the way we do that is we introduce an extra ancilla, which I call the pi over 4 state, which is just this superposition of 0 and 1 with the pi over 4 phase here. So now if I have any quantum computation here and I want to apply this T gate on some line, then I can do it like this. I can take an extra input in this state, pi over 4, this 1 qubit state, perform a controlled X gate, which is a Clifford gate, and do a measurement here and get output B equals 0 or 1. And then if you do the calculation, a simple calculation shows that the effect of that measurement applies on this line either t or its inverse, t inverse, according to whether b is 0 or 1. So if b is 0, t has been successfully applied and you don't have to do anything. But if t is 1, you've applied t inverse, so you want to apply an extra s, which is t squared, to turn the t inverse into a t to the 1. So you have this adaptive. So here's the input product facility, and here's the adaptive facility. You apply this gate according to the measurement outcome here, and it successfully applies this gate t on this line. So hence any quantum computation can be represented using purely Clifford operations like S and control X, so long as you have available the ability to have extra input states, which are product states of single qubit states. And so that shows this hardness result. Okay, so we've had a bewildering variety of things so far, so let me just summarize here what we've sort of indicated, and I guess I've gone through all the technical details rather quickly, so they're not the important point but the issue here is just to be aware of how the simulation properties of these classes of circuits can vary hugely according to what you do and don't allow. So it's very often quoted in the literature that Clifford circuits can always be classically efficiently simulated. That's a very common statement, but here we see that statement's actually quite wrong without a lot of qualification. So you have to be very careful of what the exact situation you're in. So here's all the cases, all 8 cases where you have a single output line. So here's the cases where you have non-adaptive measurements, and here a case where you have adaptive measurements. So the proof A that I presented first showed that strong non-adaptive measurements with general product state inputs can be simulated classically efficiently. That's in classical P. And that fills out all the rest, because strong simulation implies a weak simulation, so you get that one immediately for free. This way is much easier because standard input states are just a special case. So if this one's already easy, then these ones are going to be easy too. And then strong implies weak. So all of these just follow from that. And so all of these can be classically efficiently simulated. But now, as soon as you allow yourself the resource of making measurements and adapting to the outcomes, which, you know, from an experimentalist point of view is a trivial thing. It's no extra effort whatsoever. It's just a matter of which gates, you know, you're still doing the same kind of gates later. They're still all Clifford gates, but now you're noting what the measurement outcomes were to choose your later gates. So here, this one's still in classical P, it's still easy, but this one was sharp P hard, and hence when you make the inputs even more rich, product states, it must be at least sharp P hard as well, and this one was hard for quantum computing. So these are generally all very hard. So you can see here that, you know, just to point out a couple of comparisons, how slight changes of resources change the complexity of simulations. So for example, going from non-adaptive to adaptive, say from here, this is in classical P, strong, general, just simple product computational basis inputs. If you go from non-adaptive to adaptive in the same situation, it turns into being very hard, sharp P hard. And similarly, here you just go from a weak simulation to a strong simulation, and everything else stays the same. You go from something easy to something being very hard. So you get this great diversity of complexities. So this is all the cases for a single line output, and one can play the same game for many, many lines of output. So I don't think I'll go through any of the proofs of any of these things, but I just want to sort of, discuss a couple of cases just very generally. So here's exactly what we had before from the previous slide for single line outputs. And here's the table for multi-line outputs. And I worked many of these out recently with Martin van der Nest, and I think some of them perhaps don't even appear in the literature anywhere as yet. So in particular, if you first look at the adapting circuits, where you can adapt later gates according to measurement outcomes of previous ones, that's pretty much the same. If something was hard already for single line outputs, it's surely going to stay hard and probably get even harder for multi-line outputs. So we're not interested in whether it actually gets harder or not. We're just interested in whether you can do it easily or not classically. So if you can't already do it easily here, you can't do it easily here. But surprisingly, this one for multi-line outputs still remains easy. And this follows easily from the stabilizer formalism, but I won't go into the proof of that. In the case of just unitary circuits where you don't make any measurements, you just have Clifford gates, you get a couple of surprising things. So this one here, which is classically easy, so strong simulation, computing probabilities with input product states, kind of the richest thing you can have there, but just unitary circuits is easy here, but as soon as you allow many lines of output, it becomes sharp P hard. So again, you get this rather surprising jump of complexity from a fairly harmless looking generalization. And similarly, this one, where you only want a weak simulation, which is what the process itself, the quantum process gives you, this one becomes hard as well, but in a more subtle way. So for people who know what these things are, one can show that if you could classically efficiently simulate this, then an infinite tower of complexity classes called a polynomial hierarchy would collapse to its third level. So that's another one of these very implausible classical collapse properties, like P being equal to NP, although slightly different. So this provides strong evidence that already in this context, if you have input product states, many lines of output, and just a weak simulation, that quantum process already provides situations which can't be classically simulated efficiently. Okay, so we have this complete list here now, and very rich variety, and this is just meant to illustrate how rich this idea, this notion of classical simulation is as a mathematical tool for studying relationships between classical and quantum computing power. So let me not discuss those. And just go to the summary at the end. So we've seen that classical simulation of quantum circuits is a very specific and precise mathematical tool for studying the relationship between classical and quantum computing power. Even in the context of these very simple kinds of computations, Clifford circuits, there's a whole variety of variants showing that the complexity of the simulation can change very discontinuously with changes in resources. So it's a very complicated situation, the relationship between classical and quantum computing power. And there are many further issues one could explore in this context. You could consider other classes of circuits, not Clifford ones, say match gates or commuting circuits. There are other ones that already occur in the literature, and there are lots of interesting processes. You can ask the question, what's the least minimal additional quantum resource you need to throw into the situation you've already got in order to regain full quantum computing power? So, and these additional resources can turn out to be very modest, minimal things, but they can be viewed nevertheless as essential resources for quantum computing power, because without them, the quantum process can be classically simulated, but with them, you regain full computing power. So there's a whole variety of further issues here, and it sheds a lot of interesting light on specific technical issues of how quantum computing works in comparison to classical computing, and there's a lot of work that remains to be done in sorting out these things. So perhaps I'll stop there, and thank you for your attention.
Questions?
So I'll make a comment which I'm sure you're quite well aware of, but it's I think, interesting note to the audience, and that is Manny Camille, when he went to look at linear optics quantum computing, because he'd actually proved the earlier thing about the Clifford gauge. You know, he was trying to prove that there was no way to do linear optics quantum computing. And of course, they threw the measurement problem in there, and all of a sudden, they found that the general quantum computation capability came back. So it's kind of an interesting little thing is that he went about to prove the opposite of what he found. And just because of that adaptive measurement, the full power was recovered.
That's right. I guess that's true. So that's kind of in the same spirit as these extra conditions, although the linear optics gates are not quite exactly Clifford gates, but it's another interesting context of having a context which is not completely powerful and then adding this extra ingredient of adaptation. It's